Okay.
Sheaf theory and this.
Okay, so my aim today is to explain Tamarkin's approach to the Fukaya category in the particular case of cotangent bundle. But before entering the subject, I want to complete maybe a few things of yesterday. So I don't recall. So yeah. So M is a manifold, and you have the bounded Dirac category of sheaves. And so the singular support of F is a closed conic co-isotropic subset. It was not my aim to explain the co-isotropic today. Maybe tomorrow. We shall not use it, but it's important. So it's important because it shows you that it's related to the symplectic structure because it's co-isotropic. If you construct things which are not co-isotropic, they have little to do with the symplectic structure. But it's conic, so it's the homogeneous symplectic structure. Okay. So yesterday I give I just want to complete what I've done yesterday before to enter the other subject of Tamarkin. Okay. So I explained very briefly yesterday the operation of direct image, and I had no time to speak of inverse image. So, as I said, to such a situation, you have these two maps, Fd and F pi, and the projection on excuse me. Yeah. So the first theorem yesterday was as follows. You take F on M and assume, so I recall what I said yesterday, that small f is proper on the support of F. Then the microsupport of the direct image is contained where you expect it to be in this set, which is closed by the properness hypothesis. Because as I said, F proper on support of F is equivalent to saying that F pi is proper on Fd minus 1 the macrosupport of F. So why I insist on this point is because when you want to make inverse image, no more direct image, then this is much more symmetric. In algebraic geometry, when you make inverse image, you assume F is smooth in general. But it's too strong in hypothesis. So theorem for inverse image. So assume, so one says F is non-characteristic with respect to G, which means Fd is proper on F pi minus 1 of the macro support, singular support of G. Then, so you see it's very much more symmetric. No. Then there are two things. The macro support of the inverse image of G is contained where you expect it. And there is another thing which can be made also symmetric, because if F is proper on F, then, as you know, I don't always write the Dirac, the symbol for Dirac functor. Everything is derived. So the direct image is the same as a proper direct image, of course, because it's proper. Okay. But for inverse image, in this case, you have something similar. In this case, you have the extraordinary inverse image, which is isomorphic to the usual inverse image, tensorized by, I don't remember, some relative dualizing complex. I never know in which sense, this one or the other one. So it's very, you see the situation is very symmetric for direct image, inverse image. That's the macrolocal point of view. Macrolocally, you just have a Lagrangian correspondence, and you don't care if you take direct image or inverse image. It's just macrolocal correspondence. So a natural question, but I will not answer to it now, will be what happens if you are no more proper or if you are characteristic. Okay? Then I don't say anything. I just say that there exists theorem, but I don't say more now. Maybe I can explain tomorrow. I'm not sure you are so much excited about that. But it's more difficult. You need a normal Whitney normal cone. So there is a whole technology. You can give a bond to the inverse image, for example, in the characteristic case. Okay? But it's something complicated. But it has a lot of application in PDE. But okay, so that was just to complete what I said yesterday. But in fact, I will speak of Tamarkin's approach. And Tamarkin uses a characteristic inverse image, a non-proper direct image. He's obliged to use all the technology, but it's very I prefer to explain the general ideas and not to enter too much in the techniques. Okay, so now let's take this off. Now let's go to Tamarkin. So he has written a paper on archive, very long and extremely difficult to read. And I will speak of the first part of the paper, the abstract part, which gives a criterion for non-displaceability. After that, he applies it. So there are, in what I have said, there are two restrictions. One is that we work on a homogeneous symplectic or conic. On the second one, we work on cotangent bundle, not on symplectic manifold. Okay. So with Tamarkin, what I will say now, we remain on T star M, but no more homogeneous. So how to keep right of the homogeneity? There is a very well-known trick. In fact, that so the trick is to add a variable which will play the role of homogeneity. So we look in T star M cross T star R, and we restrict. So I will denote by T tau, the symplectic coordinates on T star r, and I restrict myself to tau positive. And then there is a map to T star m to x psi t tau. You associate x psi over tau. Let's call rho. So if you have something in T star m, you take the inverse image, it will be conical with respect to the xi tau variable. Okay? So it's very classical, but I must say that in the complex case, I did it with Polycello to make the link between macro-differential operators. It's out of the subject, but just to make the link between macro-differential operators and deformation quantization operators. And in this case, tau for macro-differential operator, it will be more or less d over dt. And h bar, which appear, is tau minus 1. So the h bar, which appears in analysis, can be interpreted as a factor of homogeneity. Okay? And Tamarkin told me that it was when reading my papers that he had his idea, but he forgot to mention it. But okay, so anyway, it's well known from specialists. Okay, so the idea of Tamarkin is to work here. But what does it mean? Because we work in tau positive. So now we need something well known also, which is localization. So we were in dB. Let's come back to Km for simplifying the notation. But now we have the notion of macro support. So we can localize this category with respect to the macro support. Okay? So if Z is a closed conic, if you want, doesn't change, subset of T star m, let's denote by dBz Km the full triangulated category consisting of sheaves F with macro support contained in Z. On setting U the complementary of Z, we can define the dB Km U as a localization dB Km localized by dB Z Km. So maybe everyone knows perfectly what it means, but nevertheless I recall. It means that the object of dB Km U are the object of dB Km, but now the morphism, there are much more morphism because there are much more isomorphism. Now, if you have a morphism F in G, a morphism in dB Km, then it will become an iso in the localized category if, when you write you complete this as a distinguished triangle, and if the macro support, singular support of H is contained in Z. So we have a nice triangulated category. We have a notion of macro support in this new category, because it doesn't change. Okay. So maybe now I can give. So the the main idea of Tamarkin is to work in this category. So I change the notation for short. It's my notation. It's not Tamarkin notation. It's not a good notation, but it's not worse than Tamarkin's. So I add a new variable, t, and then I localize in tau positive with respect to the dual variable. Okay? And moreover, if you have a subset A in T star M, so recall the map rho T star M cross T star tau positive R to T star M x T psi tau gives x psi divided by tau. Then if A is a subset of T star M, denoted by dB A k m tau, the dB with macro support contained in the inverse image of A k m cross R tau, tau positive. Okay. So that the main is not finished. The story is not finished. It's the first step in Tamarkin construction. So the
Example or a comment as to what tau positive gets for you?
okay, I will give many examples. Maybe you are right. I have to follow my notes. But maybe, yeah, let me 1 second before, okay?
Sure.
I forgot this. Okay, so the localization is something very difficult to handle because the morphisms are very complicated. So there is something easy, a nice lemma, but which makes things much simpler, is that we can, yeah, I have been very sketchy in my notes. So first a parenthesis, convolution. So we shall make convolution with respect to the t variable. Okay. So when you have an M cross R, you have 3 maps. The projection on S of x t t prime is x t plus t prime. Then you can make the convolution of Sheaves, define the convolution f star g as the direct image of inverse image of f tensor inverse image of G. Okay. Okay. So the what is the nice fact is that the localization dB k m. I take the whole notation to avoid confusion. So this localization, which is a localization, I recall this is dB k m cross R localized by dB with macro support contained in tau negative k m cross R. Okay. So the good news is that this is also this quotient admits an orthogonal. This is also isomorph equivalent to the left orthogonal left orthogonal in a triangulated category means F belongs to the left orthogonal means to some star left orthogonal means that F G equal 0 for any G in this thing. Okay. So this is contained. So it can be viewed as a subcategory of usual sheaves. So it's no more a localization. It's a subcategory of this category. And moreover, there is a projector.
Is it a full subcategory?
Please?
Is it a full subcategory?
Yeah, sure. All, yeah, otherwise. So, moreover, there is a projector. And the projector is, so I will write it again here. It will be also the right orthogonal, but I use the left one. And there exists, this is also isomorphic. There is a projector to this left orthogonal, which is a convolution. The projector is a convolution by this constant shift and T positive. So this is isomorphic to the set of sheaves on M cross R, such that the natural morphism, when you make the convolution, I write this, of course, I mean the constant shift with the other variable. So when you have a, so this is isomorphic to F, because F, the convolution with T equals 0 is identity with the delta function. Okay? So you have a natural morphism from sheaves on T bigger or equal to 0 to T by this map, K T bigger than 0 to K 0 to the delta function. So this natural morphism is an isomorphism. So now we have a better way to understand this category. These are sheaves which are invariant by positive translation with respect to T. So it's much nicer. And I can give examples. Okay. So I look at sheaves such that F convolution with T positive is isomorphic to F. So I will make pictures. Okay, so I give examples. First, maybe it's not an example. First, I can send, it's not exactly an example. I can send by a fully faithful functor the category of sheaves on M to the category, to the Tamarkin category by sending F to F external product with a constant shift and T positive. Okay, it's not exactly an example, but it's important. So let's give other example. So I will make picture. Maybe here I have X. Of course, for my picture, I will take one variable in X. And here is psi X. So this is T star M. And this is M cross R. Okay. And recall that you have a map from T star M cross R tau positive to T star M. So let's take some stupid example. So let's take, for example, the sheaf, the constant sheaf t bigger than x. So it should be invariant by t positive. Okay. So when I take this map rho, what do I find? So here is psi x. So I will find the Lagrangian manifold psi equal 1. So it's not conic, it's a line, but it's not a cone. That's the macro support. The image by the map rho of the macro support of k t bigger than x intersect to positive.
Where it's 1 because the slope of the line is 1.
That's the slope, yeah. That's the slope. Maybe another example is a little more sophisticated. So I don't give equations, it's just intuitive. Take something like that. So it's x on t. Then here, x psi, you will find, I think, something like that. Okay. Another example with compact support now, because it will be important. So I say the sheaves have to be invariant with respect to translation in T. But it's not exactly, it's a little sketchy to say that. I want F isomorphic to F convolution with K T positive. So I give you such an example. Take this sheaf. So here again I am in xt. Okay. So this is a constant sheaf on this locally closed subset. So it's invariant by convolution because it's the difference of two sheaves which are invariant by this convolution. Okay. And if you calculate the macro support, you see it's okay. So I have made the calculus. So the macro support in x in the xi plane will be something like that. This singular Lagrangian. You see, you have all conormal on this conormal, on all conormal here. So at the singular point, it will be these two sets. You see, you can follow the conormal. It's a good exercise for students. Okay, so it gives you an idea of what is this category. Okay, maybe. So there is a lot of technologies that I will not develop, but a few words of technology. In sheaf theory, we always use kernels. So maybe I recall briefly what it means. When you have, let's say you have three manifolds, yeah, I don't know if, yeah, but I need, no, I am obliged to do that. It's not very exciting, but it's necessary, okay? So let's, for short, let's call M1, MIG, MI cross MG. So assume that you have a sheaf K1 on M12, K2 on M23. and you have the projection M1, 2, 3, M1, 2, M1, 3, M2, 3, so Q1, 2, etc. Then you define the convolution or composition as the direct image by Q1, 3 of Q1, 2, minus 1, K1, tensor Q2, 3, minus 1, K2. That's the classical language of kernels, which appear everywhere in mathematics. So in the situation of Tamarkin, there is this T variable which plays a special role. Then one has to modify the kernels. So for so now if we work in the category, Tamarkin category, then the kernel adapted to this category is a little different. So it's a little technical, I'm sorry. So you have to make the same procedure, except that with respect to T, you make a convolution. So the formula you take is you have M12 cross R cross M23 cross R. So you have a kernel here, K1. Here you have a kernel, K2. And you have the S addition with M12 cross M23 cross R. Here you have M1, 2, 3 cross R. And finally, you project M13 cross R. So the formula you put is the direct image with respect to Q13, the last one, of the tensor product of the direct image by S of Q1, 2, minus 1, K1, tensor Q2, 3, minus 1, K2. So it's a little technical, but all the paper of Tamarkin is extremely technical. But these kernels have the advantage. You have the theorem. Okay, I do that because, of course, we need it after. It's not for fun. So it's not the most difficult. It's not the difficult part. So the theorem, take F in dB A K M tau. No, excuse me. K1 on K2 in dB B K2 3 tau. Make some hypotheses of properness for AB. So the projection, you can guess it. The hypothesis, you ask that the projection is proper. Q13 is proper on A cross M2 B. Okay. Then the convolution K1 cross K2 is well defined and belongs to A composed with B of K M13 tau. A composed with B is what you learn at school, composition of sets. the projection of the inverse image. Okay, so it's a technical lemma, which is not difficult. It's you apply the usual technique of Sheaves. Okay, so now comes, so in Tamarkin's approach, there are two big theorems. One is a separability theorem, and the second one is invariance by Hamiltonian isotopy. So the first theorem looks, it seems obvious, but the proof is very technical. So before to state it, maybe I will show you an example which at first glance seems to contradict what I will say later, but it does not contradict. So I give you an example, very, very simple. On T star R, but I work in dB kr tau positive. So it's, if you want, it's when m is reduced to a single point. Okay, so it's a base ring of the theory, if you want. So it's not a ring; it's a category. But everything that we do is over this category. So this category is not local at all. I give you this. The example, take these two Lagrangian. I work in tau positive. And I take lambda A, lambda B. So they don't intersect, okay, in tau positive. However, there exists Fa supported by lambda A, Fb supported by lambda B, such that in K, in this category Kr tau, Kr tau positive of Fa Fb is not zero. Also, the Lagrangian do not meet. Why? Because you take the Fa, the sheaf, constant sheaf for T bigger than A, Fb, the sheaf T bigger than B, and there is a morphism, which is non-zero in this localized category. Also, these two Lagrangian do not intersect. So you see that the theory is not local, and that's why it's related to Floer homology. So now the first theorem, which looks to contradict this one, but which does not, if you look carefully. So the first Tamarkin theorem is the following. Take A and B, compact in M, in T star M, and which do not intersect. Take F in dB A Km tau, and G in dB B Km tau. So I recall what it means, if you forgot. It means dB with macro support contained in the inverse image of A of Km cross R tau positive. Okay. Then the conclusion is that there exists no morphism between F and G. Okay. So it's not a contradiction because here A and B are contained in M. In the blackboard upstairs, M was reduced to 1 point, so there is no contradiction. So that's it's like in Floer homology, if two Lagrangian do not intersect, there is nothing. You find zero. No? So this is the first result. Okay, now I have to go to the invariance by Hamiltonian isotopy. So take a Hamiltonian isotopy. So R is an interval of R which contains 0, open interval. So take a Hamiltonian isotopy, non-conic. Then you can lift it as a conic. You add a variable. With in tau positive. So I have my map rho. So I can lift it as a homogeneous Hamiltonian isotopy phi tilde. So yeah, maybe I will skip some details because it's a little boring. Now I have too much. Let's call S the variable and I and T the variable of R. I have too many T because I have R on R. So there is some. You can reduce, take the direct image by take the direct image by the map T prime gives T minus T prime. So yeah, first. So when I have such a, so now I use what I have done with Kashura and Guillermo. Tamarkin used his own method, which is extremely complicated. He cut his isotopy in small pieces on glue, and horrible. But now with Kashura and Guillermo, we have this theorem that there exists a kernel K tilde such that the macro support of K tilde is contained. So let's call lambda tilde the Lagrangian associated with phi tilde. So it's contained in lambda tilde union the zero section. And K tilde restricted to S equals 0 is the constant shift on the diagonal of M cross I, R, excuse me, and so on. So you need some work. I skip the details. You define K prime first as the direct image of K tilde, where Q is a map M cross R cross I to M cross R cross I, which T primes gives T minus T prime. So now we have a shift here, and it's not finished because we want it to be invariant by translation. So we set K equal K prime convolution with T positive, and we have our kernel. Okay, but there is something. Okay, so make a break here, and I need, or maybe I should have done it before. I need to introduce some notion, so another notion. Yeah, maybe I'm not well organized because it stopped the rhythm of my talk. But okay, so now I make a parenthesis. I need to introduce the notion of torsion objects in dB K M cross R here.
Sorry, I'm
Yeah.
missing something here. So was this a statement of a theorem?
Please.
Was this a statement of a theorem?
No, it's the beginning. I have not finished.
Oh, okay, fine.
Okay. No, what I can say is that K, when you compose with K, K is a K lives here. Okay. Okay. Maybe I can go a little further. For G contained in I, so let's denote by Kg. Let's project this to K M cross R by the projection. I call it again Q. Then it will be the direct image of K that you cut by the interval G. So it's a kernel. So this kernel, Kg, will send dB Km tau to itself. And I want to obtain a result with this kernel, interesting result. So I need to make a parenthesis to explain what is a torsion object in this category. So it's the definition, Tamarkin's definition. F is torsion if there exists C bigger than or equal to 0, such that the natural morphism from F to F. So I recall that F is isomorphic to F convolution by K T bigger than 0. Okay. So F is torsion if there exists C such that F, when you take the convolution with it, when you translate it if you want, if this map is 0. That's a torsion object. For example, if F has compact support with respect to T, then it's torsion. Okay? If you remember my example, this is torsion because this has proper support with respect to T. Okay, so now I can state the theorem. I'm sorry if it's complicated, but it's less complicated than in Tamarkin. So the main lemma, if you want, is that if you use the kernel A closed in A and open in B, or K A B applied to F, then these are torsion. I could explain with more details why, but it's purely geometrical. And what I should have said is that the torsion objects are a triangulated category. So now I introduce a new category. Let's call it tau M for Tamarkin as the localization. So remember, I was on M cross R tau positive, and I localize by torsion. Okay. So you see, if I take a kernel half open, half closed, then it gives me torsion object. So it follows that K Ks composed with F and Kt or Ka, maybe to be coherent with my notation, composed with F are isomorphic in tau m. In other words, the category tau m, Hamiltonian isotopy gives isomorphism in this category. Okay. So now, oh, it's yeah, it's. I've been too fast. No, I define restriction to A. Yeah, 1 point. I should have put A with a bracket. I define Kg for G an interval. Okay, so Ka means K. Okay, so it's a little technical, but finally, theorem. I resume what I've said. You take F in dB in a Tamarkin category, the first one, on psi, phi, capital phi, a Hamiltonian isotopy. So phi is a family of phi t. Then there exists a quantization, I call that psi s, or with my notation it was ks, which are with the following property. So take f supported by a. Okay. Then you have two things. Psi s of f is supported by the image, by the Hamiltonian isotopy of phi s of a. This follows from the section on kernels, if you remember. I explained you that kernels operate on the Tamarkin category, okay, and change the support like that. That's the first point. On the second point is that psi s of f is isomorphic to psi t of f modulo torsion. Okay. So now we are more or less done. So if you want,
I'm confused with what
yeah.
S is.
Oh, yeah, excuse me, I've never said. S is something in I.
Just
Any point. It's a parameter. The phi was defined, was a family T in I, okay? So S is S is, yeah, T is not a good notation because there is another T. Huh? It's a little confusing, yeah. Okay. So you can, I will explain the non-displaceability, how it follows immediately from these two results. But before to explain non-displaceability, you can think at the Fukaya category of T star M as this category, the Tamarkin category modulo torsion, because it's invariant by Hamiltonian isotopy, and you have the separability theorem. If two Lagrangians do not intersect, then there is no morphism. But here it's no more Lagrangian, it's anything. Okay. So I show you why. It's an analogy. No, it's not a theorem.
This can play the role of the
Yeah.
category
Yeah.
in proofs.
But I guess, I'm not sure, of course, but if you restrict yourself to constructible sheaves, then it should be, because Fourier category deals only with Lagrangian manifold. So clearly it's not the Fourier category, it's much bigger. Because you have any coisotropic, not any, but you have a lot of coisotropic examples.
But if you restrict it to constructible sheaves,
Then it should be, but I don't know. At least it plays the same role. It's as useful as the. It has the same property as floor homology. So I explain you why you have non-displaceability. So you take F in dB A km tau, G in dB B km tau, and make the assumption for any constant positive in the Tamarkin category of Fg, when you send it to when you translate G, this morphism, the natural morphism, is not zero. That's an hypothesis. Okay. Then, theorem, the pair A, B is not displaceable, which means first that they meet, but the fact that A inter B is non-empty follows from the first Tamarkin theorem of separability theorem. He proves that if A and B do not intersect, then there is no between F and G. Okay. Okay, so that's the contrary now, but it, they are not displaceable means that for any Hamiltonian isotopy, A intersect phi t of B is non-empty. So why is that so? Maybe I don't give the yeah, it's some small, it's very easy, but I don't give the details, but it follows very easily of what I have said before. So you have this criterion. On, as a particular case, yeah, I should have said something, a remark, that when you send the sheaves on M to the Fukaya-Tamarkin category tau of M, this is fully faithful. So if you have a something compact in T star, so this applies only for compact subset. Huh? Take care, A and B are compact in T star M. Okay. So to be compact in T star M, since it's conic, means the zero section on M is compact. Okay. So it gives. So this implies Arnold non-displaceability theorem, because you take the constant sheaf on M, and it will, of course, satisfy this hypothesis. Okay. But the proof I gave yesterday was much more easy. But so I think I finished. But so what is interesting, of course, I think, is not the non-displaceability theorem. First, it is known. Second, we gave a very shorter proof. But it's the fact that you have an analog, or maybe of the Fukaya category for T star M. Okay. So it was not really informal.
Great, thank you very much.
Yeah.